Let's talk about derivatives of trig functions. I'm going to start by deriving the derivative of f of x equals sine of x. I can use my limit definition to find the derivative. I need to take the limit as h goes to 0 of f of x plus h, which is sine of x plus h, minus sine of x all over h. Now, if I were just to plug in h equals 0, I would get 0 over 0, one of those indeterminate forms. So instead, I'm going to use the identity for sine of a sum of two angles. So there is an identity that you probably saw in trig class that says sine of a plus b is sine a cosine b plus sine b cosine a. So I've applied that identity right here. Sine of x plus h is equivalent to sine x cosine h plus sine h cosine x. And then we still have this minus sine of x all over h. Now I'm going to regroup these terms so that I can actually work with this. So I'm going to rewrite this as two separate fractions. I'm going to put the sine x cosine h minus sine x all over h as one fraction. And then plus, we'll then have sine h cosine x divided by h. And we're still finding the limit as h goes to 0. So all I've done is reordered the terms and split this up into two fractions. And the reason I've done that is because now I can find the limit of each piece separately. And in that first fraction where we've got sine x cosine h minus sine x in the numerator, I've got a common factor of sine x. So I'm going to factor sine x out of the numerator in that first fraction, and I'm left with cosine of h minus 1 over h. And we can find the limit of this as h goes to 0. And then we're going to also find the limit as h goes to 0 of sine h cosine x over h. And to find these limits, so first term, we've got this sine x, and the limit as h goes to 0 of sine x is just sine x. There's no place to plug in that h equals 0. And then we're left with limit as h goes to 0 of cosine h minus 1 over h. And this is actually one of those common limits or special limits that we learned about earlier in the semester when we were talking about limits. And in fact, the limit as h goes to 0 of cosine h minus 1 over h is equal to 0. That's one of our special limits. I think I have that discussed in the video that talks about the squeeze theorem. And then we can do something similar with that second term. I've got limit as h goes to 0, sine h cosine x over h. That cosine x, that doesn't have any h's in it. So the limit as h goes to 0 of cosine x is just cosine x. And then we're left with that sine h over h. And again, this is one of those special limits. The limit as h goes to 0 of sine h over h is 1. And this expression simplifies down to cosine x. So the derivative of f of x equals sine x is actually cosine x. And if we take a look at the graph of sine x, I have that shown in red right here. I'm highlighting it with my pen. This is the graph of f of x equals sine x. And then I have graphed in blue, I'll highlight that one right now, f prime of x equals cosine x. And we can see that there is actually a relationship between these two waves, where the slope of the tangent line of sine x is equal to the cosine value. So for example, I can see right here that's actually at pi over 2. My sine wave has a horizontal tangent line or slope of 0, and that's a place where cosine, or the derivative, is equal to 0. Now, that was a long process of deriving that derivative. And so for most people, we're just going to memorize this. The derivative of sine x is always equal to cosine x. And you can do a similar derivation to find the derivative of cosine x, and it turns out that is negative sine x. So these are two derivatives that we're going to memorize. Derivative of sine x is cosine x, derivative of cosine is negative sine. And we can actually use those derivatives to find the derivative of our other trig functions. So if we have the function f of x equals tangent of x, that's the same as sine divided by cosine. Tangent is sine divided by cosine. And now I can actually use my quotient rule. The numerator, the top, f, is sine x. The bottom, the denominator, is cosine x. So f prime, the derivative of sine x, is cosine x, and g prime, the derivative of cosine x, is negative sine x. Plugging this into my quotient rule, I'm going to take f prime times g, so cosine x times cosine x, minus g prime times f, minus negative sine x times sine x, all over g squared, cosine x squared. This simplifies down to cosine squared x plus sine squared x divided by cosine squared x. And there is a trig identity, the Pythagorean identity, that says cosine squared plus sine squared is equal to 1. So we can rewrite this as 1 over cosine squared, which is the same as secant squared of x. So the derivative of tangent of x is secant squared of x. Now, that proof wasn't quite as challenging as the first one, but for most people, again, I think it is going to be easier to just memorize the derivative of tangent x is secant squared x. And in fact, having these derivatives memorized is going to help you when we move on in the course, and especially if you're planning on taking Calc 2 after this. So I have the other derivatives of our other trig ratios written down. You can derive these using the quotient rule as well, but the derivative of secant x is secant tangent. The derivative of cosecant x is negative cosecant x cotangent x, and the derivative of cotangent x is negative cotangent squared x. One thing to notice when you're trying to memorize these is there is a pattern. All of the trig functions that are cos, like cosine, cosecant, cotangent, have negative derivatives. And the derivative of secant and cosecant are pretty similar, just the cofunctions. And then the derivative of tangent and cotangent are pretty similar. One is a secant squared, the other has a cotangent squared and is negative. Now that we know the derivatives of our 6 trig ratios, we can use these derivatives in combination with the other rules that we've learned about finding derivatives. So for example, if I want to find the derivative of f of x equals x squared sine of x, this is a product. The x squared is being multiplied by the sine x, so I can use the product rule. My first function is x squared. I'm calling that f. So f prime is 2x. My second function, my g, is sine of x, and that has a derivative of cosine x. So I'll plug that into my product rule, f prime times g plus g prime times f, and I get 2x times sine x plus x squared times cosine x. And that is my answer. We can't simplify this. I'll just leave my answer like that. All right, let's do another one. Let's see if we can find the equation of the line tangent to f of x equals cosine x divided by x squared at x equal pi over 2. So for this problem, I'm going to use my quotient rule. The top, the f, is cosine x. The bottom, the g, is x squared. So f prime, derivative of cosine x, is negative sine x, and g prime, derivative of x squared, is 2x. Now I'm going to plug this into my quotient rule, which says f prime times g minus g prime times f all over g squared is my derivative. So I'm going to take f prime times g. So I'm taking negative sine x times x squared. I wrote that as negative x squared sine x minus g prime times f, 2x times cosine x. And that's all over g squared, x squared squared. So the x squared squared becomes an x to the 4th. And then I actually have a common factor of x in the numerator. So I'm going to go ahead and factor that x out. And I'm left with negative x sine x minus 2 cosine x over x to the 4th. And now that I've factored that x out, I can actually cancel my common factor of x. So I can cancel an x out of the top and the bottom. And that leaves me with negative x sine x minus 2 cosine x all over x to the 3rd. So that is the derivative of this function. Now, if we want to find the equation of a tangent line, we have to find the slope of our tangent line. And the slope of our tangent line is going to be that derivative at our point of tangency. So we're interested in our tangent line when x is pi over 2. So I'm going to plug pi over 2 into my derivative. So let's see, we've got a lot of computations to do here. Negative pi over 2 times sine of pi over 2 minus 2 cosine pi over 2 all over pi over 2 to the 3rd. Well, pi over 2, that's my 90-degree angle. So sine of pi over 2, the y-coordinate on the unit circle is 1. And cosine of pi over 2 is 0. So that means my numerator is going to simplify down to just negative pi over 2. So my numerator is just negative pi over 2. And then we have divided by pi over 2 to the 3rd. Now I've got a common factor of pi over 2, so I'm going to go ahead and cancel that common factor of pi over 2 out. And now I'm left with negative 1 in the numerator, pi over 2 squared in the denominator. That simplifies down to negative 4 divided by pi squared. How did I get that? This is the same as negative 1 divided by pi squared divided by 4. And then copy dot flip, or to divide fractions, you multiply by the reciprocal. So negative 1 times 4 over pi squared. And that's how I got the slope of my tangent line. So my slope is negative 4 divided by pi squared. So negative 4 over pi squared. Now the point of tangency has an x value of pi over 2. I'm going to get the y value by plugging pi over 2 into my original function. So I've got cosine of pi over 2 divided by pi over 2 squared. And cosine of pi over 2, cosine of 90 degrees, is 0. So now, using my point-slope formula, I should get y minus 0 equals the slope, negative 4 over pi squared, times x minus pi over 2. And that's the equation of my tangent line. I just removed that y minus 0 and replaced that with a y. And there's the equation of my tangent line. Finally, I did graph these two things so we could kind of check or verify our work. So this curve, it's in red, I'm highlighting it right now, is the graph of f of x equal cosine x divided by x squared. And then in blue, and I'll highlight that one right now, in blue is my tangent line. And I can see that they line up perfectly at that point of tangency, and that tangent line is just touching the graph at x equal pi over 2. As always, let me know if anything in this video is unclear.